Okay. Good. So that gives us that over here. Okay, so now let's start plugging in even more detail. Now we can plug in even more detail because we can plug in specific formulas. For example, what would be our specific formula for the initial gravitational potential energy? Well, that would be mgh initial. We've seen how it's important to think carefully about the subscripts. I need a subscript on the height because the height is something that can change in a problem from initial to final. I don't really need a subscript on the mass though, because usually mass doesn't change. So our gravitational energy would be mgh initial. Well, let's do that for the rest of our terms. Let's go through those one by one and think carefully about who needs subscripts. So what would be our next term?
1/2 mv initial squared.
Yeah, because the velocity is something that oftentimes changes. Let's keep going. That's good.
And then 1/2 I omega squared.
Now let's stop and think for a second. Which of those things is likely to change during the problem?
The omega.
Oh yeah, maybe I didn't hear you. Oh, so yeah, I didn't hear if you said initial for that. Okay, so we should say omega initial squared because the angular velocity is going to likely to be changing. Okay, good. All right, let's do the right-hand side.
Okay. Equals mgh final. I'm sorry. Yeah.
That's good.
Plus. Sorry, I have to write down at the same time. 1/2 mv final squared.
Good.
And then plus 1/2 omega final squared.
What you said was omega final squared. We should be 1/2 times I.
Oh, that's right.
Times omega final squared. Make sure you put the I on the left-hand side too. 1 second.
Okay.
Okay. All right, and then we'd continue plugging into this formula. All right, you can see this looks kind of complicated because there's 6 whole terms. It seems like this would be a lot of work. However, fortunately, on many of these problems, many of these terms end up being 0, and things end up being a lot simpler. So let's review a couple other ideas that might be helpful to us. Suppose that we have an object that is motionless. If the object is motionless, what would it be its translational kinetic energy?
0.
And what would be its rotational kinetic energy?
0.
Because if it's motionless, it's not translating or rotating. If it's motionless, it's not translating or rotating, so it would have no kinetic energy. Remember, the kinetic energy is your energy of motion. Kinetic means motion. So very often, the problem is either going to start or end with the object being motionless. Now remember that they won't always say explicitly that it's motionless. You have to look for places where it's implied that the object is motionless. But whenever it's motionless, that term would be 0, and then you can just cross it out at this stage. You don't even have to plug in 1/2 mv squared. If you know that something's motionless, you can just plug in 0 for that term, or just leave it out altogether. Now here's something that's more subtle. How about if you're focusing on an object in the instant that it changes direction? Suppose that an object is changing direction, and the instant that it changes direction, what's its kinetic energy?
It's 0.
Good. Why is that?
Because its velocity is 0.
Yeah, so that's something we've discussed a number of times in the past. When you change direction, the instant that you change direction, your velocity is 0. Well, if you're not moving, then we just saw that the kinetic and the rotational energy would be 0. All right, and again, the problem might not say specifically that the object is changing direction, but it might be implied by the problem that in either the initial or the final position, it's in the instant of changing direction. So you have to watch out for situations like that for when you can plug in a 0. One more thing, suppose the object is on the ground. If the object is on the ground, what does that tell you about the potential energy?
That it is 0.
Because the height is 0. Good. Okay. So there's many situations where oftentimes you'll be able to plug in some zeros. All right. Now let me give you one more trick. I don't think we talked about this before. There's a relationship between the translational speed and the rotational speed. and it's this equation. I don't think we talked about this equation before. Maybe I forgot. But if you know the angular speed, you can multiply by r to find the translational speed. Or if you know the translational speed, you can divide by r to find omega. So this is a very useful equation because this lets us get rid of some of the variables. So you almost always have to use this equation together with conservation of energy. So I'll write them together here. Usually we need to use these two equations together because that allows us to have fewer variables. Instead of saying omega and v, we can just put everything in terms of, we can figure out omega from v or vice versa. By the way, when you use this equation, it's very important that omega, do you remember what are the units for omega?
That's radians per second.
Good, that's good that you remember that. So there are other units, but those are the standard units. You have to use those standard units when you're using this equation. In particular, you got to use radians. You have to have omega in terms of radians in order to use this equation. So you might have to do a unit conversion there. Okay, so that's again something important. Another point to make is anytime you do one of these problems, obviously you want to draw a picture, a nice big picture, and then it's crucial to label the initial and the final points. You can't use this equation unless you're very clear in your mind about what the initial point is and what the final point is. That's an important problem-solving technique. And let's see, one more thing. I think in the past we've talked about when do you use conservation of momentum and when do you use conservation of energy. Do you remember what are the conditions when you usually want to use conservation of energy to solve a problem? Do you remember that?
When you use energy when there's like one object over a period of time, and then you use momentum when there's like two objects and they have a collision or brief separation or something like that.
That's right. So we talked about how those are probably not the full scientific definitions of when to use conservation, but those are good enough for an introductory course like yours. So yeah, so we want to use conservation of energy when we usually we use conservation of energy, not always, but usually when we have a single object and we're looking at it over a somewhat extended period of time. Okay, so maybe let me give you a problem now then. Does it make sense so far?
Uh-huh.
Okay.
Well, actually, I'm a little bit fuzzy on the when to plug in the velocity equals r times omega, but I mean, maybe it'll become clearer as we
Sure.
work it
Well,
out.
let me give you an example. Suppose I tell you that v initial is 5 meters per second and that r is 6 meters. How would you go about calculating the kinetic energy? Well, to calculate the kinetic energy, you would just plug in 5 for v, right? Mm-hmm. But how would you find the rotational kinetic energy? You'd have to know omega. Well, how could you find omega in this case?
Divide 5 by 6.
Okay, so that's how this would be useful to you if you're trying to use this equation. Very often on the problems, so the point is, on the problem, they have to tell you either v or omega, but they don't have to tell you both. So if they give you v, they expect you to be able to figure out omega using this equation. Or if they give you omega, they expect you to be able to figure out v using this equation. Does that make sense?
I see.
Okay. Mm-hmm. It would be redundant to give you both v and omega, so they usually won't do that. But we need both of those for the problem. Okay, any other questions?
No.
Okay, so let me give you a sample problem. A solid cylinder with radius 5 meters rolls down an inclined plane. Of length 10 meters. The plane is at a 20-degree angle. What will the cylinder's speed be at the bottom? With the solid cylinder, radius of 5 meters. Okay, yeah, a solid cylinder with radius 5 meters rolls down an inclined plane of length 10 meters. The plane is at a 20-degree angle. What will the cylinder's speed be at the bottom of the plane? Go ahead and tell me when you got that copy.
I have it copied.
All right, very good.